Thank you for the introduction, and I'd like to begin by thanking the organizers for the invitation. The talk will be mainly based on this work, which came out in December of 23. But the general ideas behind this development are contained in these series of papers. So the idea that a large N gauge theory reorganizes into a string theory has a long and fruitful history, which dates back from 't Hooft and coming to full bloom in the AD-CFT correspondence. And in particular, perhaps the most basic statement of this dictionary is that a state labeled by gauge invariant words in a large N gauge theory is dual to a state consisting of closed strings propagating in a bulk spacetime. So a whole lot about the large N thermodynamic properties of ADS string theory can be learned from the above statement, especially at weak 't Hooft coupling, thanks to these works. And so this is because at lambda equals to 0, the partition function of a UN gauge theory, which counts gauge invariant states on S1 beta cross S3, reduces to a unitary integral over a holonomy matrix U. Okay, so the large N saddles of this matrix integral correspond to the thermodynamic phases of the bulk and the stringy regime. And so when f of q, which is the single letter partition function, is taken to be that for a superconformal index in a superconformal gauge theory, these saddles are interpreted as a sum over BPS families of Euclidean black holes. So the main question I'll be addressing in this talk, or at least made progress towards a basic understanding of this question, is what happens to the statement that I mentioned before. A state labeled by gauge invariant words in the large N gauge theory is dual to a state consisting of closed strings propagating a bulk spacetime when N takes a finite integer value. So at finite N, there's an apparent tension regarding the spectrum of states of the bulk and boundary theories. In the boundary gauge theory, the states that you form by exciting the vacuum with single trace operators are orthogonal at large N, but become constrained by trace relations when N is finite. So for example, if you're not familiar with these trace relations, at N equals 2, a single 2x2 matrix valued scalar X satisfies the trace identities, which forms an infinite tower starting from degree 3. So every trace with X with power greater than 2 can be decomposed into a sum over sums of products of lower traces. So the total number of states from the boundary gauge theory point of view should decrease as N is decreased. But on the other hand, in the bulk, non-perturbative states such as black holes and D-branes become lighter at finite G string. And here I've drawn a picture of what I can conceive of, all the objects that I can think of in the bulk. So such objects which are present in addition to the perturbative string states would naively result in many more states at finite G string compared to those at small G string. So how do you reconcile these differing expectations? So to avoid a paradox, it's typically posited that non-perturbative objects in string theory represent highly redundant descriptions of the same set of quantum states. And this phenomenon has to happen so much so that the non-perturbative effects actually need to cut down the total number of states. And this comment is not restricted to any particular BPS sector. It's just the general expectation. The expected upper bound on the single string spectrum is called the string exclusion principle that we talked about, and that was talked about in the previous talk. So while this principle is thought to be a generic feature of string theory, there's little quantitative understanding of the mechanism underlying the principle. So it's a name that's given to a phenomenon that we don't quite fully understand. Uh, the giant graviton expansion, which is a recently proposed formula that relates the BPS sectors of gauge theories and their string duals, it suggests how the stringy exclusion principle might be realized in the bulk string theory spectrum. And it takes this general form, which I'll show a particular example of very soon. So Zn of Q, which is the supercontrol index of a UN n equals to 4 superang mills, reorganizes into a sum over BPS indices of ADS 5 times S5, labeled by K giant graviton branes. So let me explain the terms. Z infinity is the index of K, S5 Kaluza-Klein modes. And this factor is the index of K branes and their open string excitations. Okay, so pictorially, this sum you can understand as such. I've drawn the sphere because a giant graviton is a D3 brane in the context that I'm talking about. So it's a BPS D3 brane on R cross S3 inside ADS 5 times S5. And it's supported via a large angular momentum induced from the background Riemann-Roman potential, C4. So to illustrate its basic properties, let's just stare at the formula in the simplest half BPS example. Okay, so the half BPS sector in UN n equals to 4 superang mills is a purely bosonic sector, which consists of these operators, just sums of products of traces and their powers. Modulo trace relations at finite n. Counting its spectrum is simple, and it gives the left-hand side. Two conspicuous features of the bulk side of the formula are shared in all other examples of the giant graviton expansion. So number one is the absence of contributions, explicit contributions from supergravity saddles. Yes?
What is Q?
Q is in this half BPS context, Q is a fugacity for the particular R charge of U1 isometry corresponding to a U1 isometry on the S5. Okay, there are 3 independent such U1s. So the second feature is the alternating sign in this bulk side of the formula, which results in large cancellations of degeneracies. So, so despite the absence of explicit supergravity saddle contributions, it was shown by these authors that the asymptotic degeneracies from bulk giant gravitons in the formula reproduce the entropy of large 16th BPS black holes in ADS 5 times S5. So this formula, as was explained before, exhibits lots of cancellations among the brane terms. And so therefore the saddle is not on the real, saddle of the sum is not at a real value of K. It's actually at an imaginary value of K. But nevertheless, summing the saddles of this sum, one can reproduce the leading large black hole entropy. Okay.
So just going back to the previous slide.
Yes.
Is there such a formula for 1/16th BPS black holes for 1Q?
Yes. Oh, 1Q.
That's what I see in
the
formula.
No. So one has to scale, as you know, the fugacities in a particular way to see BPS black holes.
So you have multiple.
So yeah, this is a simplified version of the formula that I'm showing here for illustrative purposes. But in general, there will be 4 independent fugacities, which are scaled in the same way.
Yeah, but have we managed to write the simplest formula with 1Q?
The construction that I'll be showing you produces exactly that,
okay,
this. So
okay, so that's something new, right? Yeah.
Yes.
Yeah, thanks.
What is the formula for the entropy of the 1/16 black hole?
So one can write down a formula for the free energy in terms of the chemical potentials, and yeah. There are other experts. I mean, Samir is an expert in the audience who can answer this question much better.
But I don't know what you want. It's n squared times a particular function of the charges. You want the function. The function of the charges roughly goes as the charge to the 2/3. And if you want more details, you should do it after that.
Thank you. So observe that in each sum end, supplemented with the half BPS Kaluza-Klein spectrum, overcounts the half BPS spectrum of UN n equals to 4 super Young Mills. So each of the sum ends, if you expand, will overcount the left-hand side. But this overcounting is saved by the overall minus signs, -1 to the k, that appear with odd numbers of, or the signs appear with odd numbers of D3 giant gravitons. So BPS spectra on ADS5 times S5 labeled by different numbers of giant graviton brains exhibit large cancellations to reproduce the finite end result. And this is a realization of the string exclusion principle. These cancellations occur even in the purely bosonic half BPS sector, where the index is equal to the partition function. So I'll argue in my talk that the -1 to the k does not originate from the usual fermion number grading -1 to the f inserted in the index. And indeed, recent path integral calculations of Euclidean D3 giant gravitons show that -1 to the k arises due to the need to rotate the contours for 2k unstable bosonic modes on the world volume. And these modes are present both in the one-loop partition function and the index of the Euclidean brane. And in total, they contribute the prefactor -1 to the k for the contribution of k coincident branes. So in this talk, I will show that the states of bulk D3 branes possess a form degree grading via canonical quantization of its open string modes. So the procedure that I'll discuss here, which was given in this work, won't be enough to fix the overall sign. But it'll give us an option to associate a sign. This is where this approach lacks in comparison to the Euclidean computation. And we'll fix this sign using a boundary computation. By matching the spectrum of D3 giants with the spectrum of finite and trace relations on the boundary, we'll see that the signs -1 to the k from the boundary perspective are a consequence of properly accounting for finite and null states via a BRST procedure. So now let's find the BPS states of D3 giant gravitons on R cross S3 in ADS5 times S5 via canonical quantization of its open string modes.
Can you go back to your formula of expressing? Can you provide some physical intuition as to what is going on the left-hand side and right-hand sides in terms of the giant gravitons?
So I mean, the left-hand side is the gauge theory result. Okay. So you simply count the number of independent operators composed of these traces acting on the vacuum, and this is what you get. The right-hand side has an interpretation in the bulk in terms of a sequence of spaces labeled by different giant graviton branes and open string fluctuations on them.
What is the interpretation of little k?
This little k, it'll play the role of the number of these giants. So you have a sum over different backgrounds, and you have to count all of these giants.
May I ask a question on that
Yes.
slide?
Yeah.
Actually, sorry, maybe you can go on.
Okay. So we'll work in ADS5 times S5 coordinates, covering, this actually covers half of the 5 sphere, but it'll be convenient to work in this coordinate with Raman-Raman 4 form potential. And R is a polar coordinate on the transverse plane to S3 and S5. And we'll be interested in the maximal D3 solution, which sits at the center of ADS5 And it's a limit of stable solutions, this was worked out by them, as r going to 0 and this theta dot going to 1 over L on the S5. And this is a BPS classical D3 solution, which has energy n over L and angular momentum n. L is the radius of ADS. So we're interested in the half BPS transverse fluctuations of this brane on a maximal S3 and S5 fixed on the U1 isometry. And this is the bosonic dBi plus Chern-Simons action on a single D3 brane. The classical solution and its energy was worked out in early 2000s, so I won't review that, but I will proceed directly into the one loop fluctuation contribution. So the quadratic action around this maximal solution, just focusing on the transverse fluctuations of S3 into S5, is given by this. You get an extra term coming from the induced Riemann-Roman four-form potential in these complex coordinates. So the fluctuation fields possess the time-dependent phase compared to those in the usual n equals to 4 Super-Yang Mills action on R cross S3. Okay. So the world volume gauge, let's take the A equal to 1, 2, and B equal to 3, 4 world volume gauginos to have R charges plus half and minus half respectively. So and the total action for the fields that possess these charges, the R charge, relevant R charge is given by this. And this action has an interesting property. So half of the SUSY spinners on R cross S3 involved in these transformations are world volume time independent, while the other happen to be world volume time dependent. So time independence of these spinners is usually taken for granted on R4, but it happens only for very specific forms of the action on R cross S3. So maybe to emphasize this point, note that the usual action of n equals to 4 Super-Yang Mills on R cross S3 has time-dependent supercharges. So Q would actually increase the energy on this manifold. So this means that the Hamiltonian on the world volume theory of this D3 commutes with half the supercharges, or that the generator of world volume time translations is a supersymmetric Hamiltonian with respect to this half. So the ground states of HD3 are BPS states because one can find that the Hamiltonian differs by a unit of the R charge from the stationary frame Hamiltonian, generating translation of with respect to the global time of ADS5 times S5. So HD3 is the supersymmetric Hamiltonian, whose ground states are the BPS states. It's the twisted Hamiltonian. So for half BPS states, it suffices to consider a supersymmetric quantum mechanics given by consistent truncation to the lattice S3 modes, because the higher modes do not satisfy the BPS condition. And from now on,
There's a question.
yes.
Stupid question. So I have a giant graviton. I have an S3
Yes.
hurtling around the equator. On the S3, I have two equators. I have two U1s. So your states are having. I don't understand what.
So, the maximal giant that I'm considering here is completely stationary. So the world volume does not move.
Does not move.
But this is because it's a maximal giant.
Oh, it's a maximum. Okay. So it's polarized to the.
It wraps a maximal S3 and S5.
Mm-hmm. And then on that S3, you have this fermion zero mode. You're doing this quantization on the S3, and the fields you are having do they have angular momentum in the other?
No. Oh yes. Yeah. So in general the fields. So for example, you'll have 4 directions in the ADS5. So this brane sits at the center of ADS5. You have 4 independent scalars
in the ADS5.
in the ADS5 direction, and then you have 2 scalars on the S5 direction, which are transverse to S3 and S5.
Okay. And
Okay.
you have a gauge field on the word volume also.
That's right. But
Okay.
for this analysis, I'm not going to consider them
Okay.
because they don't contribute to the half BPS sector.
Okay.
In the Euclidean path integral calculation done more recently by, namely by Beccariac and Cabot-Bizet, they consider all the modes on the branes and in the Schur sector, and they reproduce the Schur sector
I see.
results.
So your half BPS states on this giant graviton, do they have angular momentum on the, so I have an S3 word volume of this D3 brane. I have two U1s in the S3. Do they have angular momentum on these U1 directions?
Angular momentum in the which
So-
direction?
So I have an S3.
Yes.
The S3 has two U1s inside.
Yes.
Has two equators.
Yes.
Do your states have an angular momentum on these equators?
No. So
No.
the states I'm considering right now, so the half BPS states don't have this spin along the world volume, the
I
Lorentz
see.
spin along the
I
world
see.
volume.
I see. So they are still half BPS in a sense. They are still they only have
Yeah.
one angular momentum from.
So right now I'm for this talk I'll mostly consider in the half concentrate on the half BPS sector.
I see. And you don't have any angular momentum in ADS either.
No.
Your scalars in ADS. Okay.
No, it
Okay.
won't.
Okay. Thanks.
Only along the transverse direction of S3 and S5.
Okay.
Yeah, if they're transverse directions, then yes. Yeah. Okay, so this is the world line action that happens to be relevant for describing just the half BPS excitations of a D3 giant. Okay. So this is a supersymmetric quantum mechanics, which has this Q and Q dagger, which can be identified with the Dolbeau differential and its adjoint. And namely, these differentials are those which are deformed by an inverted Morse function. So this can be just worked out from this action. Okay. So then the Hamiltonian of the supersymmetric quantum mechanics is the deformed Hamiltonian, the deformed Dolbeau Laplacian. And we pick a representation for the fermions given by deified bar and the contraction on differential forms. So the BPS states are the eigenstates of this operator with 0 eigenvalue. So this system was studied in depth in the context of holomorphic Morse inequalities. So this function H induces a vector field which generates an isometry of C with fixed points at the critical points of H. And near any fixed point, this Laplacian deformed by this inverted Morse potential takes this form. And where this LV is the Lie derivative with respect to the vector field V. So this just contains some terms that don't involve derivatives with respect to phi. Okay, so from this you can read off the induced vector field by looking at the term with the Lie derivative, which coincides with the U1x isometry generator up to a sign. Okay. So this sign reflects the change in the orientation of the U1 action acting on the normalizable state due to sitting at a local maximum of H. So there's a prescription discussed in the paper that I mentioned. Since V generates an isometry of the phi plane, this Laplacian and the Lie derivative commute. And so we can find the relevant BPS states by finding solutions to this equation. In the small radius limit, so we've only considered the quadratic action, right? But actually, so therefore, to justify the solutions that we find, we need to go to the small radius limit. So within each LV eigenspace, a fixed charge M. So why is that? Notice that this 1 over L plays the role of the angular frequency in a harmonic oscillator, which you can crank up arbitrarily if you're considering a term that's Q exact. And here the Hamiltonian was Q exact.
Sorry, what was L in the giant graviton?
L was the ADS radius. So first we've decomposed the modes into the spherical modes on S3. And then after having decomposed the modes and looking at the zero modes of the bosons, I'm arguing that it's possible to consider just a quadratic action in this limit. So although in general we do not expect to trust the dBi action in this limit, because we've decomposed the fields into the modes, for the zero mode, I'm arguing that you can, essentially the Gaussian wave functions should be sufficient.
You answered my question before I asked it, but you're saying that even though the geometry is strongly curved when L goes to 0, the Hamiltonian is still a reliable.
Yeah, because the harmonic term is becomes the dominant term. So I've already decomposed into modes on S3. I'm taking the limit after having decomposed into these modes. Okay, so anyway, so the dominant potential forces all BPS states of fixed charge to be localized near the fixed point for any given m in this limit. And so the BPS states of D3 giants localize to fixed points of bulk isometries in the small radius limit. Okay, okay. Maybe I should have mentioned this after showing the wave function, but okay, I'll show it shortly. So taking this limit is within the regime of validity for the world line quantum mechanics truncated to the lowest modes, because we take this limit after decomposing fields. So to find the normalizable states, we allow this deformed Laplacian to act on the space of differential forms. And these are the wave functions with zero eigenvalue. There's a tower of them. Their R-charge spectrum is given by the action of the Lie derivative for M0, 1, 2, and so on. So this tower gives the half BPS spectrum on a single giant that we expected from the giant graviton expansion in the half BPS sector, where Qn, which I didn't compute explicitly in this talk, accounts for R charges carried by the D3 giant. And here we introduce a fugacity mu for the form degree. And this coincides with the k equals to 1 term of the giant graviton expansion in the half BPS sector if we set mu equal to -1. But this procedure itself doesn't determine this mu. So you may note that there's a shift in the R charge of the open string vacuum associated with this single giant relative to the classical expectation of n. And so why was this there? This shift resulted from the fact that the open string vacuum on a single D3 is labeled by the anti-holomorphic 1 form. And you can generalize this construction to the k by k Hamiltonian, which is expressed in terms of these eigenvalues. And we can do so by finding form-valued and UK invariant solutions to the supersymmetry conditions. And to just show the result, this is the wave function where this wave function is labeled by M1 through MK, which takes values in this expression. And these states have these R charges. So the half BPS spectrum of k coincident giants is this. So this is the kth term of the giant graviton expansion in the half BPS sector. And there's again a shift due to the fact that the states were K forms. So finally, let's start comparing these results to the boundary. So far we've seen that the open string vacuum on K giant graviton branes is labeled by a differential K form. And this form degree equips the bulk open string Hilbert space with a grading, which is seen to coincide with the number of coincident wrapped D3 branes in ADS 5 times S5. However, the half BPS states on the boundary and UN n equals to 4 superrang mils on R cross S3 are scalar valued because the corresponding Morse function, you can do the same procedure, does not admit any unstable direction. So if you do a similar analysis, you'll find a sum over these symmetric group, this expression, namely it's not a form valued wave function. So this forms the basis of half BPS states for the boundary UN n equals to 4 superrang mils. And you can compute their R charges and you get the expected result in the half BPS spectrum. So the grading with respect to the form degree of states does not appear in the physical half BPS Hilbert space of the boundary n equals to 4 superrang mils. So the obvious question is, how are these form-valued states of D3 giants in ADS 5 times S5 encoded in the boundary UN n equals to 4 superrang mils? To answer this question, we need to identify the states in the boundary gauge theory that possess some grading and also reproduce the spectrum that was computed on the world volume of giant gravitons. So actually identifying such states is made subtle because as shown above by explicit computation of the half BPS wave functions in n equals to 4 superrang mils, these states cannot belong to the physical Hilbert space of the gauge theory. So how are they encoded in the gauge theory? So we can obtain clues regarding the nature of these states by examining the mode expansion in Z of the determinant operator, determinant Z minus X. X is the relevant scalar here, inserted at a point in UN n equals to 4 superrang mils. This operator is dual to a family of D3 giant graviton solutions wrapped on S3 and S5 with order n units of an R charge. And this Z is an auxiliary parameter which has an interpretation as the bulk insertion point of the brane on the plane transverse to S3 and S5. This is an auxiliary parameter which is not related to the insertion of this determinant in the gauge theory. So the fluctuation modes of these determinant operator are given by this expression.
Sorry, can I ask?
Yes.
Rewind for a second.
Yes.
So from the gauge theory point of view, Z was what?
Sorry?
From the gauge theory point of view, Z was what?
Z is an auxiliary parameter which controls the, it's an auxiliary parameter that you can introduce as part of a determinant.
Do I have to introduce it? Can I set it to
You
0?
don't,
Okay.
but it'll be illuminating as I'm showing here. So, well, typically determinants are associated with giant gravitons in the bulk. So the first few coefficients of these PNs is given as such. And you may recognize that these tower of modes in quotes starting at Pn plus 1 are but the trace relations between gauge invariant operators that are present in any UN gauge theory with the complex scalar X. Okay, so in other words, states constructed by acting with these null modes on the vacuum are the finite and null states. And so while these null states yield the correct half BPS spectrum, if you count them on a single D3 giant, we shouldn't identify them with the side of trace relations directly with the bulk D brane states. And so Why is that? The states need to possess a grading that we saw from the form degree of the states in the half BPS sector in order to explain the overall signs that appear in the BPS spectrum of K coincident wrapped D-branes. And no such grading distinguishes the finite and null states from the physical states. So instead, I propose to identify the BPS D-brane states with auxiliary ghosts. So these are additional ingredients with dimension and R charge starting at n+1 in a boundary U infinity gauge theory that compensate for null states due to trace relations that would have been present at a finite value event. So how does this construction go? So the effect of introducing these anti-commuting ghosts along with the homological charge Q hat acting in this manner is to reduce the U infinity gauge theory to a UN gauge theory. So I'm converting, all I'm doing here is a change of variables. And the word homological and not the cohomological, rather than the cohomological, is there because that's what's conventional in the math literature. It decreases the ghost number for these auxiliary fields. So these auxiliary ghosts should be distinguished from the BRST anti-ghosts that you introduce for gauge fixing in a UN gauge theory. Rather, the role of these auxiliary ghosts and the differential is to supplement this U infinity theory with directions for systematically removing all but the UN degrees of freedom. Okay, so it's simple to compute the spectrum with ghost number K in the half BPS sector because this sector does not have ghosts for ghosts. Any other sector will. The states with ghost number K are multi-ghost states built out of K chi's. And we can write a basis of these K ghost states as such. So with this range of values for the A sub i's. And this yields the charge spectrum which agrees with the bulk computation of the BPS spectrum of K D3 giants. Here, these signs must be included because the ghosts chi are implementing null relations here.
Sorry.
Yes.
How by hand is that?
This was a change of variables that was
Yeah.
purely done by hand. Okay.
Yeah. So you're essentially promoting these trace relations to a set of operators. Can I think of it
Yes.
this way?
So I'm embedding the UN gauge theory
Yeah.
into a U infinity gauge theory, but introducing extra ghost fields to compensate the effect of that the trace relations would have had.
So the -1 to the K needs to be there in the construction for this to actually give you back the UN gauge theory.
That's right. That's right. It needs to be there. So this form degree labeling the states of K coincident giants should be identified with the ghost number K of auxiliary ghosts that compensate for trace relations in the boundary gauge theory.
If I want to compute a Witten diagram in ADS 5 times S5, should I now be worried that there are ghosts D3 branes that I should somehow deal with?
Are you talking about ghosts or D3 branes or ghost D3 branes?
I understood that you want to think of some of the giant gravitons as ghosts. Is this incorrect?
Yes, which is different from ghost D3 brane. Yes. That's what's indicated by the giant graviton expansion.
Some of the giant gravitons are ghosts according to your proposal, right?
Ghost in a finite n
In a finite
gauge
n,
theory,
in a finite
yeah.
n gauge theory.
They play the role of these ghosts which implement trace relations.
Okay,
That's the argument.
now I want to calculate the Witten diagram in ADS 5 times S5. Typically in gauge theory, in theories with ghosts, I should consider the ghosts
Yes.
in the calculation.
Yes.
Should I also consider these ghosts in the Witten diagram calculation now?
For a thermal thermal observable, so I'll show a dictionary that you get by construction, which is coming next. So there is a prescription for computing thermal observables as an alternating sum. It's called the Lefschetz trace formula in the BRC formalism. And
I was hoping to get a yes or no answer.
I don't think these contribute to expectation values on the vacuum, but these would contribute to a thermal observable. Okay.
About this k variable, or the k quantum number, in the box, should I think of it as the fermion number?
So it's a fermion number which is different, which I'm arguing is different from the F, which is 2R in the boundary gates theory.
Yes, so from the boundary, k has no meaning, but in the box, can I identify it with the fermion number?
Oh, not a physical fermion number, but it's a fermion. It's a Z grading which is labeling these vacua built on.
I see.
Yeah.
So in the bulk there will be two fermion number in this case.
Yeah. In this picture, yes. There are two fermion numbers in the bulk. If you're interested in computing the index.
Small comment on the Witten diagram question. That's a semi-classical amplitude, so at infinite n, these things go away. So I think the answer is no. But this is at finite n, we can't talk about a finite set of Witten diagrams. So certainly in any one diagram, they're not there. That's what I would think. But yeah.
So maybe it's worth emphasizing that I'm identifying the form degree which labels the vacuum with the auxiliary grading introduced for these chi's for trace relations. So not all fermions appearing in a perturbative wave function have representations as differential forms. Fermion appears in the wave function as differential form if its scalar partner parameterizes an unstable direction of the Morse function. So a reflection of this fact is in the Euclidean brane path integral is that -1 to the k arises in the one loop partition function. So even in the one loop partition function, not the index, due to the 2k unstable bosonic modes on the world volume. So what does the identification between these half BPS states of bulk D-branes and the auxiliary ghosts in the suitably rewritten boundary UN n equals to 4 super n mils suggest about the bulk half BPS space of states? Well, so we can organize the space of multi-ghost states with coefficients in the ring of polynomials of traces into a complex. Okay? So where Vk is the space of multi-ghost states of ghost number k with coefficients in the ring R. And H infinity is the half BPS space of states of n equals to 4 super n mils at infinite n. And Q hat is an operator which acts via the graded Leibniz rule on these ghosts. So the comparison of the spectrum suggests that Vk should be identified with the perturbative space of states built on ADS 5 times S5 in the presence of k coincident half BPS giants. So this complex has non-vanishing homology only at 0 ghost number. And since the image is the space of trace relations, so remember that we introduce a ghost for every trace relation. So this would be the space of trace relations with coefficients in R. The homology at ghost number k equals to 0 is the Hilbert space of the half BPS sector of UN n equals to 4 super n mils at finite n. Okay? So let's observe that each Vk in the above complex is a Fock space, which was not necessarily, which would not necessarily be the case for a general finite n space of states, built from these multi-ghost generators with coefficients in R. So namely, Vk are free R modules. So this means that if we augment the complex with H sub n, the space of states that we know at finite n, in the final step, this resulting exact sequence is called a free resolution of the half BPS space of states H sub n at finite n. So roughly speaking, a free resolution is a procedure of replacing a highly constrained space H sub n with the sequence of unconstrained Fock spaces whose generators represent the constraints on H sub n. And this resolution gives a precise relationship between the half BPS space of states H sub n of un n equals to 4 superangle at finite n, and this complex, which we identified as being composed of bulk half BPS space of states of type 2B string theory and the large curvature limit of ADS 5 times S5. So you can understand each component of this complex in terms of this picture that I showed in the beginning of the talk. This resolution says that it implies that open strings on bulk D-branes are encoded in the relations between the single trace generators that arise in the boundary gates theory at finite n. So namely, it's encoded in these open strings on these particular D-branes are encoded in the trace relations. So let's recover this familiar expression in the half BPS sector. So it's a property of exact sequences that the alternating sum of the dimension of spaces in the complex vanishes. So we can express the charge spectrum of H sub n in terms of an alternating sum of the charge spectra of Vk over K0, 1, 2, and so on. So this is a relation that is a consequence of the fact that this is a exact sequence. So this alternating sum formula shares its origin. So it's not, it's a very familiar object in 2D CFT, appearing in the BRST approach to minimum models on a torus. So the space Vk of kth order relations, kth order trace relations in our context plays the role of the space of Virasoro descendants of singular vectors in 2D CFT, where you can have submodules inside submodules for which you have to take the alternating sum to collapse into the final answer. In that context, you're also using the BRST approach to account for null states. So in both contexts, -1 to the k arises from an auxiliary grading that's unrelated to the physical fermion grading. So as a trivial consequence of the computation that we've already done, this yields the half BPS giant graviton expansion. And the fact that it's a free resolution, the complex is a free resolution, explains why the closed string spectrum would be factored out on the right-hand side, because Vk are free R modules, and Z infinity is the partition function over of just H infinity, meaning that the result would factorize into the Hilbert series of coefficients and the Hilbert series of the generators themselves. So what's the bulk interpretation of the differential Q hat? So the Q hat maps a half BPS state of K coincident D3 giant to linear combinations of states of K-1 coincident D3 giants with coefficients in the traces, where this is a trace relations of charge n plus A. So a natural interpretation for Q hat in this construction is that it's an instanton that interpolates between a pair of open string vacua labeled by K and K-1 wrapped D-branes.
Question?
Yes.
So if I've understood some steps in this, though, there are some unstable directions on these D3 branes?
They're unstable modes in the Euclidean D3 brane calculation.
Right.
Yeah.
So in the bulk computation, you would say there's some open string modes that are tachyonic?
In the Euclidean picture,
Yeah.
yes, yes. So,
So
there is a so if you look at, say, the single particle partition, one loop partition, if you extract the single particle partition function from the one loop result,
Yeah.
one loop determinant, you would see a 1 over q. Okay, so that's a sign that you need to analytically continue the contour for only the relevant modes, which are
Right.
unstable.
Right. So there's an old story 20 or more years ago about condensation of open string tachyons and unstable branes. So can this be shoehorned into that language of, so there was a story where you could get sort of, there, how to say this? There again, there was some complex associated with multi-D brane states, and then some relations that were given by tachyon condensation. In the end of the day, you were only interested in the stable branes. And this sounds a little bit like that in the sense that you're saying there's a relation between a KD brane state and a K minus 1D brane state that's somehow related to perhaps condensing these unstable modes in the Euclidean theory?
I'd love to understand that further.
Okay.
So I'd love to talk about
All right, maybe
talk
later.
about this. Yeah. So the lessons from this half BPS sector that we've beaten to death is the following. So we can identify the bulk space of states in the half BPS sector with the complex of auxiliary ghosts, which implement the finite and trace relations via Q homology. This Q hat, which doesn't have to do with the supercharge. This complex furnishes a BRST-like resolution of the finite n space of states in the boundary gauge theory. So while the bulk computations relied on supersymmetry and having a large, having a weakly curved gravity limit, I want to argue that the lessons above do not rely crucially on these properties. Trace relations between gauge invariant operators are present in any finite n gauge theory with adjoint fields. And at least when lambda equals to 0, we can always write the space of states of such a theory as that of a U infinity gauge theory, supplemented with these auxiliary fields for trace relations that would have been present at a finite value of n. But in more general circumstances, so if your single trace generators are given by more complicated set of matrices acting on the vacuum, the trace relations will satisfy non-trivial relations among themselves. And so computing this resolution requires introducing ghost for ghosts, and as in the BRC formalism. And the algorithm for computing such a resolution is called the Kozel-Tate resolution. So assuming that one has computed the Kozel-Tate resolution up to some energy cutoff, one always has to work with the energy cutoff because we have not classified the relations between trace relations. The Lefschetz trace formula relates the trace taken over Hn with an alternating sum of the traces taken over Vk. So the free thermal partition function of a UN gauge theory on S1 cross S3 is equal to the alternating sum of the free thermal partition function over Vk of the Kozel-Tate resolution. This procedure always has to be done with the cutoff. So the thermal correlation functions are related in this manner. For superconformal gauge theories with non-anomalous R symmetry, we can write in addition the relation between the superconformal indices. where the CIs are conserved charges that commute with the supercharged Q. So I suggest that the Lefschetz trace formula provides a gauge string map at lambda equals to 0 and finite n, which I would love to check it, to have the tools to check it. So the bulk observables are computed by taking the alternating sum of the expectation values in an ensemble of states built on each open string vacuum, which are these VKs. And so the tools available now only allow us to compute BPS quantities in the large lambda regime and then to extrapolate those quantities to lambda equals to 0 for comparison to gauge theory computations. But it would be nice to compare the gauge and string theory results directly at the free point in the future, perhaps by analyzing conformal boundary conditions of tensionless strings in ADS5 context, although there's a long way to go. So in this talk, I've shown that the half BPS space of states, the spaces of states, VK, of perturbative fluctuations of ADS5 times S5 with K-wrapped D3 branes at various K form a complex which furnishes a free resolution of the half BPS Hilbert space of UN n equals to 4 superrang mils at finite n. And this suggests that the open strings on certain bulk D branes in ADS5 times S5 are encoded in the finite n trace relations between the single trace operator in n equals to 4 superrang mils, rather than being encoded in physical operators. So this space is encoded in the failure of the finite n Hilbert space to be an infinite n Hilbert space, which can be systematically studied. So I've also explained how the causal Tate resolution and the Lefschetz trace formula provide a starting point for probing the gauge string dictionary at lambda equals to 0 and finite n. And I hope we can apply these lessons to understand dynamical properties of the bulk at finite n, which I would like to make progress on. In particular, trace relations exist at finite lambda. And so how does the structure of this resolution change when you turn on the coupling, and what additional ingredients are required? Maybe some ideas along these lines would be to combine the tools from Chiming's talk in this context. And is there a path integral formulation of the complex with an action written in terms of the gauge invariant variables and these auxiliary ghosts? I've only sketched an operator formalism in a very particular simplest sector, which is the half BPS sector. But I wonder if there's a path integral formulation. And how do we describe the dynamics of these ghost states? And how are properties of black holes encoded therein? So yeah, thank you for these for your attention, and that's the end of my talk.
Thanks for the nice talk. Let's start the questions.
June, thank you for your talk. I know you're aware of what I'm going to say, but perhaps not the rest of the audience, so I just want to say it. So with my student, Giorgo Eleftheriou, and a postdoc, Marti Roselio, in Taiwan, both of whom are very talented, we developed a bulk interpretation of the main formula that we discussed in a paper that we put out in January.
Yes, I'm very aware.
I think it's very relevant to the talk you just gave. It's a bit of a shame you didn't refer to it. I didn't want to interrupt your presentation, but 10 minutes are allotted discussion. I thought I could take 2 minutes to give a gist, but if there are other questions, I'll wait for them. It's very quick. So there are many things that need explaining from the bulk. So firstly, there's a whole moduli space of half BPS giant gravitons, like what Josef was asking.
So
there's a sphere, and the giants can have various sizes, and then the giants can also puff up in ADS. So this index so we think of the calculation of the half BPS index. The index can be written as a path integral on the space and the space of fluctuations of gravity and the branes. And then there's a supersymmetric localization that happens that localizes onto the maximal giants. and their quadratic fluctuations. That's the theorem of localization. And the quadratic fluctuations have a very nice expression. It's a supersymmetric version of a lambda problem, which you can exactly solve. That has both bosons and fermions. And if you put all of those things together, you get exactly the main formula. Thank you.
Thank you. Yes, there's a work by Samir later in December discussing the first part of this talk, which was the bulk computation. I think while our results agree, I would disagree with the interpretation of your result, because you obtain, in your paper, you obtain these minus signs by converting from the functional integral formalism to the Hamiltonian formalism and defining a world volume F. However, I would argue that actually these minus signs need to arise purely from the bosonic modes. And this is supported in the Euclidean brain path integral computation, because if you evaluate the one loop, just the one loop determinant for the bosonic modes, you get a minus sign in front by the need to analytically continue the contours of 2K unstable bosonic modes. So for this reason, I think I think while our results agree, I would disagree with their interpretation of our results.
I don't see why what you said. I don't see why what you said says that my interpretation is incorrect. But I think we should postpone this kind of a discussion.
To hear more about that out there, Shimei.
Yeah, so if I want to go beyond half BPS, and so for half BPS, Q just annihilates the latter, so I mean the supercharge action is just trivial. But if I want to go beyond half BPS, and then I would think that we need to consider something like a double complex and consider cohomology problem of this double complex.
Right, with your Q and the Q hat here.
Okay.
Yes.
And you would think that the correct differential to consider would be the Q plus Q hat. Is that the right thing?
I guess that's typically the right thing.
Okay.
But
Okay, thanks.
we should talk about it.
A comment is that there is no bulk when lambda is equal to 0. I would recommend you to forget about this problem. There is a well-defined gauge theory description at lambda equals to 0. There is no bulk. That's
Well, it's just a highly stringy limit of the bulk.
there is nothing. It's
Is there one? I thought I saw one. No? All right.
So I'm still a little bit confused about these unstable modes. So if I was to start with K coincident giant gravitons, are you saying that there's some, as K increases, there's some increasing number of instabilities of those things?
Yeah, there are 2K unstable bosonic modes. So yes,
And it wants to decay to what?
so that remember these unstable modes appear in the Euclidean brain calculation. So I'm not sure what it would decay to in real time, but
Okay, but does that mean it's like a sphaleron?
I'm not sure. I don't know what that is. So yeah.
The remark is, these are just supersymmetric giant gravitons of the type that most people in this room know. There's no instability, there's no physical instability. So I don't think there's a relation to the tachyon condensation you're talking about. There may be a relation to sphalerons. That's very interesting, because in the Euclidean theory, you have to define a contour.
Well, let's thank Hoon once again.